This is a transition update. In this update, I'm going to talk about the work that I did to finish all the attempt all the problems in section 25, which is finite groups, finite simple groups, and then back to the main story of the book, back to rings. And so altogether, this is a September 30 update. I'm at 426 proofs, 840 problems attempted, and that is 49.8, ever so close to 50%. So, of course, I have already read section 12, and I've completed all of 25. So in the future updates, it'll be all about rings, 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 and more rings. I'll show the book because I'm going to show the reading for section 12. So I'll first go to section 25 and just show that it's more of the same as last update, which is all about testing for finite simple groups. Of course, this chapter concludes with the fact that A5 of order 60 is a simple group. So 60 and 168 are simple groups. And I believe every single problem in this section ended out to be a proof. Yeah. So all about simple groups. And then I'll show a few problems and the reading for section 12. So now it's going to be very similar to what was done with groups, but now with rings. By similar, I mean that there's a chapter 12, excuse me, that is talking about rings, the definition of a ring. Of course, you're adding multiplication to addition. That is, you have two operations. In the case of groups, you are always either doing a multiplicative group or an additive group. Now, when you do rings, they're both, but additive is the main thing. All rings are commutative in addition. And then some rings are commutative in multiplication, and those are called commutative rings. And then there's also the business of whether it has a unity, and that means whether it has a multiplicative inverse. It is always going to have an additive inverse. And it's always going to have associativity in multiplication and what's called left and right distributive over addition. Yeah. Some examples, some rules of multiplication. Part of the proofs for these are in the problems. Then the uniqueness of the unity and the uniqueness of the multiplicative inverse. This is also a problem. And then some subrings. And that's it. And then how some of them are related to each other. So to finish off problems in, let me see if I'm lined up correctly here. I think that's better. Yeah, I think that's better. Yeah. So to finish off all the problems in section 25, it was all about various methods to show that a group is simple or not. Most of them were not simple. Yeah, so laying out Celo's third theorem, and then either doing embedding or some other theorem to say, okay, it's not simple. In this case, this is a very interesting problem where I had to find a subgroup. I just wanted to find an example. Let me see which problem it was. I may have placed this sheet in the wrong place, but it's a problem that says prove that A5 does not have a group of order 6 or 10. And sure enough, A5 does have a group of order 10, but I was unable to find one of order 6. So I'll have to figure out why I missed that, because it should have a group of order 6. In the case of problem 23, okay, it talks about a matrix group, and it's order 168, and it's the proof to show that it is simple. And one thing that was interesting is, I think I did it correctly, but in the case of the answers, they do mention specific examples of the elements of the matrices. I found that interesting, and I copied it because I was not about to spend hours and hours and hours coming up with matrices for these. I'm glad the answer in the book that it is in there. Then also another very interesting problem is that 1, 2 and 1, 2, 3, 5, those permutations generate S5. At first I stumbled and I got a little lost in how to do it, but then I realized it's really literally those two together. So now, because they're together, you can multiply them on the left or the right, and you can do 12, 1, 2, 3, 5. I mean, I'm sorry, 1, 2, 1, 2, 3, 5, or you can do 1, 2, 3, 5, 1, 2, and all of those yield different numbers. And sure enough, when you start putting in higher and higher orders of them, so of course, you put in the first bit, and then you get a new element. Well, this element is that, right? Some power of 1, 2, and 1, 2, 3, 5 in any combination. And then when you squeeze more on the right or on the left, you continually get more and more terms. I didn't do the whole thing, but sure enough, eventually you'll get S5, no doubt about it. And then the problem 25 is actually a proof where you take out the examples and you really make it down to a general format. Yeah, that was pretty straightforward. I really like that. But I still took the book's answer, what I call the clean answer, and I wrote it down just to understand. Yeah, up to isomorphism, A5 is the only simple group of order 60. I goofed this up. This is all talky talk. The way the book does it is correct because I started assuming, yeah, so it is isomorphic. I got confused. In reality, they meant to say, what you really want to do is to set up a contradiction to find something that is not isomorphic to A5, and that's how the whole proof goes. So I messed that up, but I'm glad that I learned from the book of how to do it correctly. Yeah, 29, every time I see these P's and Q's and they're modded, it reminds you of number theory, and it's very easy to set up if they're odd primes, which they are, and you know the Q is the bigger one, the Q minus P is equal to 2n, and n is a natural number. So really, that's where every time some proof is like that, that's how I hit it, just from my old number theory learning. But I still, the book had a slightly different way to word it, and I like to get two views. It's almost like learning in stereo. But I always like to try to figure out by myself before looking at the answer, that's for sure. Otherwise, what's the point? A finite group of even order that has a cyclic Silo 2 subgroup is not simple. I thought I had answered it correctly, and then when I looked at the answer, I was like, that's not where I was going. So once again, I put a question mark on this one. I'm going to revisit this one at some point. Yeah, this is a revisit. I read it and I'm like, I would have never thought of that. Okay, fine. The right regular representation of G. I was like, all right, thank you. I didn't do that. And then these other theorems where S5 does not contain a subgroup of order XYZ. Yeah, so I think the way to hit it is with the index theorem. Yeah, when you do the index theorem, but also I think, yeah, I actually ended up using the embedding theorem as well. Yeah. Okay, so that's the end of section 25. Now back to the main theme, rings. And so rings can be non-commutative, can be commutative. Either way, they may or may not have a multiplicative identity, and that identity may have an inverse or without an inverse. I think that's correct. Yes, because this is the whole business of unity. I think so. Yeah. The examples again, just drawing them. And I lengthened a little bit the steps. I put in a couple of steps that the book did not have. And then I started on the problems, and just to warm up, I learned some from Socratica. Yeah, I went back and I went to the web and I watched a few videos by Socratica, and it was great how the units are explained. The fact that the units are a group. In Socratica, she uses mod 12, and U12, the unit group, is the units of Z12. That was very interesting. Yeah, and then I also went to Benedict Gross, some of the lectures, one lecture. And of course, in Gross's lecture, he goes much further. He actually lays out the bones of all of the sections on ring theory that I'm going to cover in Gallian. But I wanted to see like a full kind of like a bird's eye view. Yeah, this is all from that gross lecture. It was very difficult to follow because the video is such low resolution that I actually had to keep rewinding just to actually write down the words. So this is actually a transcript of the lecture, almost without looking at what it says on the board because I couldn't tell. I could hardly tell what he was writing on the board. Yeah, and then I started on the problems right here. And then in the case, this problem 3, I thought was a very interesting problem. An example of a subset of a ring that is a subgroup under addition, but not a subring. Wow, what a twister. And so the book has n square root of 2. Sure enough, when you square n square root of 2, you get n squared 2, and 2 is not and it's a radical. So that's a good one. Now, I came up what I believe, and I'm going to make a note here because I plan to come back to this. I came up with non-square matrices because non-square matrices under addition, I believe are a group. You know, they are a subgroup of GL and F under addition, but they cannot be multiplied. A 3 by 2 matrix cannot be multiplied by another 3 by 2 matrix. You got to do the flip, 3 by 2, 2 by 3. So that's what I put as my answer, and I believe it is also correct. I believe non-square matrices also are an example of a subset of a ring that is a subgroup under addition, but not a subring, and the ring here being GLNF. That's what I think. Yeah, and then in the case of 4, yeah, for fixed non-zero elements, AX equals B can have more than one solution. And I was like, you know, this goes back to Mendelssohn. This actually goes back to Mendelssohn when I was reading number systems for analysis, the whole business of zero divisors. So sure enough, I did Z9, found the zero divisors, and also found, of course, sure enough, there's a whole row here, the 3 multiplication row. You'll see that 3 times 2 is equal to 6. 3 times 5 is also equal to 6. 3 times 8 is also equal to 6. This is exactly AX equals B, more than one solution. I believe so. Yeah, and then proving the unity and the multiplicative inverse. These proofs are all very similar. And I know, for example, number theory has a whole bunch of them.